sharing. Stanley, Patrick,
I'm using my phone.
Sophia,
Joshua, for me.
anyone in a position to do so. Go ahead.
Okay.
Seraphim, sinaona imeanza yako. Oh, nice.
Imeanza. Okay.
Iko sawa.
Sawa, mali
yeah, Seraphim, uko poa sasa. Yeah.
Sawa. If it stops at any point, you'll just let me know. But yeah, basically, I am sure guys had already told you the basics, what enzymes are. They're basically just proteins that increase the reaction rates of reactions, and they do that by lowering the activation energy. So they just they are just catalysts. They are biological catalysts, and as we know, when catalysts are involved in a reaction, they don't literally take part, so they are reusable since they are not consumed during the reaction. So this graph basically shows what happens during a reaction, like when there's an enzyme or a catalyst involved. It basically just reduces the amount of activation energy required. So the reactants are able to overcome the amount of energy they need to actually be converted to products. And of course, now we'll be able to apply enzymes, whether it's for metabolism, for diagnosis, or even in management of some of the conditions we'll see later on. So that's just basically it. Then there are some of the important terms that we'll need to at least understand going forward doing enzymology, and also for other units. I'm sure other people will now be talking about enzymes and substrates and whatever. So now we need to get the basics right. So for the active site, that is just a very small part in the enzyme where the substrate binds. And now a substrate is the reactant in that whole reaction. So when the enzyme and the substrate bind, then they form the enzyme substrate complex. And when enzyme and the substrate they are binding, they usually actually either fit in very well in a lock and key model, or when the substrate binds, then the enzyme might undergo some conformational change so that now the substrate and the enzyme fit perfectly in the induced model. And then also for some enzymes, they might need cofactors to maybe bind, activate them, such things. So we'll see all those things as we move on. Yeah. So an active site is just a small pocket of cleft where the substrates bind, and the substrate is the reactant in the biochemical reaction. Then when they bind, they form the enzyme substrate complex, which then the complex dissociates. It can dissociate back into the substrate and the substrate, or it can continue to form a product. And the enzyme is, of course, left unaffected. So then it can continue catalyzing the reactions. So there are two hypotheses that we look at in the whole enzyme and substrate binding. That is the lock and key model and the induced fit hypothesis. So in the lock and key model, it just assumes that a substrate and an active site on an enzyme, they can literally fit into each other. But then again, now considering how a lock and a key works, like a specific key is made for a specific lock. So then they cannot be used interchangeably. Then that would again bring about specificity of enzymes and the kind of reactions they'll catalyze. And then for the induced fit model, when a substrate binds to the active site of an enzyme, it brings about some conformational changes that now ends up adjusting the whole situation and making it at least they fit now better. If I am too fast, too slow, just let me know, we can adjust. If these are the basics, also let me know, we can move on to other things. Yeah. So then now, like we've said, since like a specific substrate binds to a specific enzyme, then there's that whole specificity aspect of the enzymes. So there are three classes of specificity. We can have absolute, group, or linkage. Absolute is when an enzyme can only be used in a specific reaction. Like the enzyme can only work with one substrate. Like urease has absolute, it's very specific to the kind of substrate. But then there are others that can work for a whole group. Like for example, the hexokinases, they would now work for any of those, the hexos, the whatever, those six structure things, the kina glucose and kina fructose. Then when you have a hexokinase, it would phosphorylate any of those reactions as long as it's that group. So it's just group specific. Then for others, they are linkage specific. So those ones are specific to a certain type of bond, maybe peptide bonds or any other type of bond. So like peptides by chymotrypsin or yeah. Okay. Then we also have cofactors. Now there are some enzymes that they are on their own, they are not, what do we call it? Let's say they are not active on their own. So they need a cofactor to bind for them now to be active. So you will need now for those kind of enzymes. So for normally would say an enzyme, a substrate, they bind, form enzyme substrate complex, dissociate to form a product, and an enzyme, or the reaction is reversible, it can form the other way around. But now for some enzyme, they also need a cofactor to bind for the enzyme now to be able to catalyze those reactions. So for such an enzyme, before the cofactor binds, the enzyme, it's called an apoenzyme. Then once the cofactor binds, it becomes a holoenzyme. Okay. Yeah. So then now these cofactors, they can be of different types, either metal ions or small organic molecules. Yeah. So for the small organic, for the metal ions, there are metalloenzymes like zinc, which is needed by carbonic anhydrase, or magnesium for hexokinase. When we'll be looking at the metabolic pathways, we'll see where we need the hexokinase and where we need the magnesium to activate hexokinase for the whole cycle to continue. So metalloenzymes are metal ion cofactors. Then we said we also have small organic compounds. Those ones are when they are also coenzyme, and if tightly bound, the cofactor will then be called a prosthetic group. Since it's not normally there, but you have to bind it there for the, what is it called? For the enzyme to catalyze that reaction. Yeah, so this we'll see when we are doing the metabolic pathways, but that's just about it. So like now here, hexokinase, we said hexokinase. Yeah, we said hexokinase is hexokinase, or even is an example of a group specific enzyme. But now for something like glucokinase, it's now a bit more specific than the hexokinase. Okay. So this table is just showing now again a few other coenzymes and the enzymes they bind to. You can just look at that. Yeah, so like we said, what enzymes do, they just lower the activation energy they lower the activation energy so that a reaction can just proceed. Like the barrier needed to be overcome for the reaction to work, it's much smaller. Okay, now we'll go to the classification of enzymes. I think that's what Gaius was doing. Gaius, was that what I found you doing? How far had you gone?
Ilikuwa ni properties.
Yeah, just properties.
Oh, okay. So now when we are naming enzymes, there are two systems, either the trivial name or the scientific name. So the trivial names are just those random names, trypsin. You just hear trypsin, you don't even know what it is, what it does. It gives absolutely no idea of anything. But then now we have the systemic names, which at least give an idea of what that enzyme does. Yeah, so now the first part of the name gives the name of the substrate, and the second part gives the type of the reaction. So for example, the glucose 6-phosphate isomerase, basically it shows the substrates, the glucose 6-phosphate, and the type of reaction it catalyzes, which is an isomerase. So just does the conversion of glucose from glucose 6-phosphate to fructose 6-phosphate. The isomers, I think we remember from last week's discussions about isomers and such. Yeah, then now the classifications. So the classification is basically just based on the type of reactions the enzyme is involved in. So we have the classes where classifications giving digits 1 to showing a class, a subclass, and such. So yeah, these are the classes 1 to 6. So class 1 is oxidoreductases. Of course, they catalyze oxidation reduction reactions. Then now, of course, then under that class, you will again see the different kinds of enzymes, the oxidases, reductases, and the others. So yeah. So I think for this, you just have to know what class has what type of enzymes. Yeah. So oxidoreductases, they just basically either hydrogen ions or an oxygen. They are involved in the transfer of either an oxygen or a hydrogen. So that is what happens during those. So there are subclasses. We have dehydrogenases, oxidases, yeah, all those. But basically for them, it's either transfer of a hydrogen or an oxygen. Then transferases, they involve the transfer of all other groups now, except hydrogen and oxygen, which then belongs to the class 1 for oxidoreductases. So like this one, we said you look at the name, then you can see what the substrate is and what kind of reaction it is. So you can just tell what is going on in each reactions. Yeah, so these are some of the subclasses for the transferases. Then we have hydrolysis. Of course, they catalyze hydrolysis. So water molecules are involved in this kind of reactions. And then lyases or synthetase. These ones, they are involved where you, they remove groups, but there's no water involved in the whole reaction. So subclasses is like the fumarase, maltases, yeah. And then now isomerases, that one we have heard about it a number of times and what it does. And the subclasses, again, will tell you if it's an isomerase, an epimerase. Do you know what epimers are from previous discussions? Epimers, racemic mixtures, and such kind of things. So for those kind of reactions, then we'd use isomerases. And finally, which are also called synthetase. Okay. So now that we have at least defined what enzymes are and looked at the few classes, okay, and looked at the few classes, then now we can at least, if you want to measure enzyme activity, that would just be the amount of substrate that was converted to a product per unit time. Yeah, and then now for substrates, for enzyme activity, of course, there are some factors that would affect enzyme activity. That is substrate and enzyme concentration, temperature, pH, inhibitors, and activators. So for substrate and enzyme concentration, of course, if you increase the concentration of a substrate, then the reaction will, of course, proceed much faster. But then again, it will only increase to a certain point until when the substrate is so saturated that, again, it has now no further increase in the reaction rate or the velocity of the reaction. So then when you plot a graph of the velocity or the reaction rate against a substrate concentration, again, it looks like that. And then for the enzyme concentration is always directly proportional to the reaction rates. And then for temperature, so each different enzymes have different optimal temperature where they, of course, work to the optimum. So when you, let's say when you are working under low temperatures and you increase the temperature, you end up increasing the reaction rate because you increase the kinetic activity of the molecules and the reaction rate increases. But then when the temperature increases beyond the optimum temperature, the enzyme is denatured and the reaction rates drop, which can even drop to stop the whole reaction. And then for pH, again, just like temperature, enzymes also have optimum temperatures where they work, like they function best. For most of the enzymes, they work best under neutral pH, that's 6 to 8. But of course, we have exceptions. For example, pepsin, whose optimum temperature is, again, acidic pH below, like between 1 and 4. So then that would be an exception around there. And then the effect of an activator, of course, now like the ones that needed, yeah, if there's an activator, of course, it works much better. It increases the enzyme activity as opposed to when there is no activator. And then, of course, inhibitors, they will lower the reaction rate, but they do not denature the enzyme. Then, yeah. So this is just basically what happens. An enzyme reacts with a substrate, the enzyme substrate complex, which then can proceed to form the product and the enzyme, or the complex can dissociate back to form the enzyme and the substrate. And then we have the reaction constant there. Yeah, so you can, yeah. So at low substrate concentration, the reaction rate is directly proportional to the substrate concentration. And then as you increase the substrate concentration, of course, the reaction rate increases until it reaches a maximum velocity, Vmax, where now even if you add more of the substrate, the reaction rate does not increase any further. Yeah, so now the reaction rate, this is now the formula for the reaction rate and everything from now, that equation and the, yeah, what is it called? Michaelis-Menten equation. Yeah. Yeah. So from what's this? Km. Km is just the, what is it called? The substrate concentration that allows the, like, yeah, substrate concentration that is needed to reach, what is that called? Half Vmax. Yeah, or something like that. Yeah. So now, yeah, come here. Yeah, so Km is the substrate concentration which permits an enzyme to achieve half of the Vmax. And we have said Vmax is the maximum reaction rate that a reaction can achieve. So when you have a large Km, then it would indicate that it indicates the need for a high substrate to achieve maximum reaction velocity, which means then that the enzymes has a low affinity for the substrates. So if you have a larger Km, you need more of the substrate to reach the reaction rates. Okay. So we said enzyme inhibition, they just slow or stop the enzymatic reactions, but they do not denature the, what is it called? They do not denature the enzyme. So now for the inhibitors, they can be of two types, either reversible or irreversible. For the reversible ones, of course, they are reversible, so we can just go back to not inhibiting and continue with our normal reactions. Then the reversible, so they bind to form an enzyme inhibitor complex, but then it's held together by weak non-covalent interactions like ionic and hydrophobic interactions, which rapidly dissociate, and then they just leave the enzyme, which can just go back to now continuing with the normal reactions. So there are three types of reversible inhibitors or reversible inhibition: competitive, uncompetitive, and non-competitive. So for competitive for competitive inhibitors, the inhibitors has a similar structure to the substrate. So then the enzyme cannot differentiate if it's the substrate or not. And once the inhibitor binds, then the substrate cannot bind. But then now for such kind of competitive inhibition, if you just increase the rate of the substrate, you can just outcompete the inhibitor and continue with the normal reactions. Yeah, so this is what it looks like. If you increase the substrate, sorry. If you increase the substrate concentration, then the reaction will continue to form the product. But if the substrate concentration is low, then the inhibitor will continue binding to the enzyme. As much as the binding is just too weak, it binds and dissociates back, but it either limits or just reduces the reaction. So when you have competitive inhibitors, they just alter the Km of the reaction, but they do not change the Vmax. And we said Km is the concentration of the substrate you need to achieve half Vmax. So if you have an inhibitor binding to that, to the enzyme, you need to increase substrate concentration to achieve the normal binding. So if you have a competitive inhibitor, then the Km is increased. So that's for competitive inhibition. They just basically have the same structure, the inhibitor and the substrate. Then for non-competitive inhibitors, they bind the enzyme at a different site from the active site. So they don't need to have the same structure as the substrate because they have a different binding site. But now what happens, once the inhibitor binds to its binding site, there's that whole conformational change thing happening, and then the substrate no longer fits to the active site. So now it will just disrupt the normal arrangements. So therefore the concentration of the substrate is meaningless, unlike in competitive inhibition, hence cannot be overcome by increasing the substrate concentration. Since they are not competing for the same active site, even if you increased the concentration of the substrate, the conformation of the active site has already changed. It still wouldn't bind. So what happens? So for non-competitive inhibitors, they decrease the Vmax, but they have no effect on the Km. So that's non-competitive inhibition. And finally, we have uncompetitive inhibition. So for uncompetitive inhibitors, they bind to the enzyme substrate complex and not the free enzymes. So once the enzyme has reacted with the substrate to form the enzyme substrate complex, then now an inhibitor binds to that complex. Once it binds, once the inhibitor binds to that complex, the complex cannot proceed with the forward reaction to form an enzyme and the product. Instead, it forms the enzyme substrate inhibitor complex. So for uncompetitive inhibitors, they lower the Km since the inhibitor binds to the complex, producing an enzyme substrate inhibitor complex. And so the enzyme substrate complex is continuously being depleted. So uncompetitive, it reduces the Km, but has no effect on the Vmax. Uncompetitive inhibitors have little effect on the reaction rate because they lower the Km of the enzyme, which offsets the decreased Vmax. Uncompetitive, they lower both the Km and the Vmax. Okay. So that's for reversible inhibition. Then irreversible inhibition, so reversible, for reversible, the reaction was able to keep switching back and forth between the inhibitor and the substrate because they were bonded by weak bonds. But then for reversible inhibition, once they bind, it's covalent bonds, which are, of course, more strong, and hence it permanently inactivates the enzyme. So irreversible inhibition will lead to a decreased Vmax and no effects on the Km. Guys, how are we doing so far? So suicide inhibitors are just a type of irreversible inhibitors. Yeah, so maybe we can just continue with enzymology and do the next part for enzymology, which was clinical enzymology. So clinical enzymology is just basically how we can apply the whole enzymology story to the clinical practice. Like, how would you use it to either diagnose or treat or something like that? So, of course, we said enzymes are specific to certain reactions. They're specific to certain substrate. And of course, and they are found in different concentrations, in different tissues, in cells, in plasma. They're found in different concentrations. So when the concentration is upset, then you will be able, and you can detect the changes in the concentration. Then now you can at least try figure out where the problem is. So that's basically what clinical enzymology is all about. So when you measure the enzyme activity, it's measured in units. Yeah, so now we're measuring the amount or the level or the activity of those enzymes in plasma. And there are those enzymes that are normally found in plasma. Those are the functional plasma enzymes. But there are those enzymes that are not found in plasma, or if they are found in very small concentrations. Those are the non-functional plasma enzymes. So for, like we said, functional plasma enzymes, they are found in higher concentrations in plasma. Of course, you'll know what they do and to what substrates and how then their substrates are always present in blood. They are produced from the liver. And so if they decrease, then of course you'll know there's a problem with the liver. or something like that. But then for the non-functional ones, they are found in the other, now they are found in the other sites and in very small concentrations in plasma. So if they are high in plasma, then you can now estimate, like, this enzyme is high in plasma, it's normally found maybe in the liver or in the heart. So there's a problem either with that specific organ, or maybe it's the clearance of that enzyme that has an issue. So non-functional plasma enzyme in healthy individuals, the plasma levels are fairly constant. So for example, for LDH, the levels are those ones, either 120, between 122 to 202 units per liter for a normal, let's say normal adults. So then if the levels are above that, then you will be able to see what's the issue. So you can be able to see we have LDH in liver, kidney, skeletal muscles, or maybe, I don't know, placenta somewhere. So then you can try see maybe there's now a problem in either one of those organs, or maybe the clearance of that enzyme has been affected. But then now again, for some enzymes like LDH, they have different, what are they called? Isoforms. So then again, you can say, of course, there's a problem, but since it's found again in many organs, you can't specifically say it's found in this one organ. So either you can also do a test of other enzymes found in that organ, or you can test for the specific isoenzyme to be able to tell it specifically what organ that is affected. So we've said the concentration of enzymes in plasma will depend either on the balance between the influx and the clearance. And the influx will be high if there is increased production from the cells, or maybe the cells have actually multiplied so much that there's increased proliferation of the cells itself, or the cells have become increasingly permeable to that, so they are just leaking the enzymes to the surrounding. But then if we have, again, if the clearance is okay, it would clear. But if clearance is also affected, there will also be an increase in the level of enzymes. So the non-functional enzymes during clearance, they are catabolized by plasma proteases before they are taken up by the reticuloendothelial system that through receptor-mediated endocytosis. So that's reticuloendothelial system, whatever, that whole thing. What is it? The liver, bone marrow, those ones. So what happens when that enzyme is in the non-functional enzyme, the one that is not normally found in plasma, now it's in plasma. So what happens? Plasma proteases will catalyze it. Then receptors will bind to the enzyme. They are endocytosed, and then they're taken up to the lysosomes and degraded, and that whole cycle. Now at least they are removed from blood and we can go back to the basal level or something like that. But then again, if we have maybe reduced, so the enzyme activity in plasma may be increased due to increase in cell permeability, increased cell death, proliferation of the cells like in cancers, or reduced clearance from plasma. And then the concentration can also be lower than normal, either maybe to reduced synthesis. Reduced synthesis can maybe due to like a drug, disease condition, or even maybe a congenital anomaly. Then you'd have a lower than normal concentration of those enzymes. So again, you just go back to figuring out if it's reduced, if it's increased, what is the problem. So for clinical enzymology, We're just trying to find what is the clinical underlying condition that is leading to this whole imbalance in the enzyme levels. So like we said, the receptor-mediated endocytosis, the what are they called? The enzymes in plasma, they are taken up, they are endocytosed in the reticular endothelial system. They go into the lysosomes, degraded, and yeah. But then, so that's receptor mediated. When they bind to that receptor, they signal there is a protein, clathrin. It binds to the vesicle. That's why it's also called clathrin dependent endocytosis. So the molecule in this case is the enzyme you are trying to clear from the plasma. So it will bind to the receptor. Yeah, the molecule binds to the protein receptor. Then it moves to the clathrin coated pit. Then the cells of the membrane folds inwards. They are endocytosed. They form a vesicle. Then the vesicle fuses with an endosome. Then it splits, so that once it splits, the part of the cell membrane goes back to the membrane, it's recycled back, and then the, what are they called? The enzymes are degraded. Yeah, so basically, that's all, what is it called? The general or the basic of clinical enzymology. So then now you just need to check now the specific things. But now for an enzyme to be used, whether it's for diagnosis, or therapeutics or whatever, we need it to have at least a longer half-life, because if it has a very short half-life, then even when you measure its levels in plasma, they'll have reduced by the time you're taking the measurement, since it's so short. So then you won't be able to detect that increase. So at least they need to have at least a higher, what is it called? At least a longer half-life, not seconds and minutes. Yeah. Then we have isoenzymes. Like we said, if you've measured a certain, like we said, LDH, and you've seen its levels are high, but then it's found in so many organs. So what you can do, you can now measure the specific isoenzyme to determine which organ is affected. For example, if you measured and LDH was high, then now you test for the specific isoenzyme that is increased. If, let's say, for example, you find it's LDH1, LDH1 is found, where, my guys? So LDH1 is found where? In the heart. So then if that's the specific isoenzyme that is increased, then at least now we come closer to figuring out exactly where the problem is. So then we can say it's the heart. Then if you say it's the heart, then now you can at least say it's the heart. Then you can also measure now the activity of other enzymes that are found in the heart to see if they are also elevated. So you can also estimate for more than one enzyme. And then also you can also do serial enzyme estimations, where you measure the activity, not just once, you do it severally, so that you can also be able to determine, is it just an acute thing? Was it just, I don't know, an error, or is it really a problem with an organ. So when you're selecting an enzyme to test, like we said, it to really consider the half-life. And then also you need to, of course, understand the distribution of that enzyme in the various tissues. Yeah, so you need to understand the enzyme, it's found in what tissues and what cells is it, yeah, so that at least when you're measuring the concentration, then you can just figure out where. So now you need to look at the distribution of different enzymes in different tissues, so then you can be able to now clinically apply what we are saying. Yeah, so these are some of the enzymes and the principal tissues they are found in, and what now their levels would clinically indicate. Guys, no one even wants to say hi.
Hi.
Mr. Lover.
Yeah.
Bombast.
Theater mnamotivate mtu manze. Nashangaa kama bado mko. Anyway, yeah. So now these are the enzymes. The enzymes, so you can measure the level of these enzymes in plasma and then see. So for example, for something like alkaline phosphatase, it's in the liver, it's in bone, in the intestinal mucosa, in the placenta. So then when you check for those levels and they're actually high, you can't just go ahead and say it's this. So then you also need to do now multiple enzyme, like you have to check for the concentration of other enzymes that are found in the liver to be able to now conclude it's for sure this. And then now again, even if you conclude it's the liver, again, different conditions would affect the concentration of different enzymes. Yeah, so then again, you'd have to check what, yeah. Yeah, my guys, I don't think there's anything I can explain on this table. You just need to know what is where and what it would clinically indicate. So you'd have to look at those enzymes, their sources, and all that. So there are some examples here of pancreatic enzymes, those in the liver, and all those kind of things. So then you can just measure the level of those enzymes. If it's high, if it's low, you can be able to tell exactly what is the issue. For example, for alpha amylase, if like the normal values are between 28 and 100 units per liter. So then if you assay and you see there is maybe an increase, then of course there would be a problem with the pancreas. So you'd have to now investigate to see what it is. So if the increase has happened just very, let's say very abrupt within 2 to 12 hours, then that would be something acute. If the levels it increased within like 2 to 12 hours, and then again within the next few hours, the levels were dropping back to normal, it was an acute condition. And then you also need to check, I mean, it's okay, we are saying there's an increase. Is the increase, what is it called? Okay, I can't find though. Is the increase significant enough to warrant an investigation into like the functioning of that organ? So if let's say there is an increase of 4 to 6 folds, then of course that you would go ahead and check. And then so we were looking at alpha amylase. So alpha amylase, it's both in saliva and in the pancreas. So if you check and the levels are high, then you can go ahead to check for the specific isoenzyme that is there, so that now you can at least see, is the problem in the salivary glands or is it in the pancreas? Then now we have others like lipases and all the other enzymes. I think for those ones, I don't know, maybe you guys would just have to know or something like that. But also, I don't know if it's me who has not sent questions, but I have not. Maybe we might see some when we are doing the revision. So now, like, for example, for the liver enzymes, let's see. Like for the markers for hepatocellular damage, you have AST and ALT. But then, of course, they will not increase like in proportional levels, or you will also find like the enzymes are not only in the liver. So you can't just assess just one of them and then say there's a problem with the liver. You have to do a number of enzymes, and if it has isoenzymes, you also have to do it. My guys, so I think the others just enzyme and the clinical significance. So you just have to know, I'd say, look at that table that we've passed over there. Look at that table, then that would be okay. So but also we look at, like, we're doing, what is it called? Specialized tissues. Like when we are talking about the liver, of course, we'll talk about the whole cholesterol thing, what enzymes are elevated, what are not. So we'll still look at some of these enzymes and their clinical implications, but you can just check out that table in the meantime. Yeah, so my guys, I think I'll take a break. But what? Hey, Bagwat. Yes.
Yeah, daktari. Niambie.
Yeah. So I think for enzymology, that's just the basics of it. Then alafu, now we can look at what's the time? Okay, it's headed to 9. We can do like a few, I don't know, you guys can just tell me what you think. We can do a few of those metabolic pathways, maybe, so that we won't have so much to do in the next 2 days, because peer biochem, it's kind of a lot or something.
So you are thinking we do one of the metabolic pathways?
Yeah, maybe we can do 1 or 2. So see, guys, you can take us through one of the cycles, then I get water, then I do 1. We can do like 2 before we enter the session.
Sawa. Hi guys, hi. Nasikia vile my voice is deep. Yeah, that's me now. Yeah. Anyway. Let me start with glycolysis, because glycolysis is the first one. Then it goes to the TCA cycle. Then we go to the electron transport chain, because that's how energy flows, right? So okay, guys, you'll excuse me, I don't have the notes, but I'll be highlighting the best parts, right? Okay. So energy. Energy is just we get energy from glucose. At the end of the day, the fat, we say the fat of everything in anything you eat eventually will be converted to glucose, right? Then the currency of energy in the body is ATP. It's ATP that we use to conduct activities such as, let's take for example the sodium potassium pump. What pumps it, or rather what it uses, is ATP for energy. Another example we can say is for muscles. Muscles. When you're in the gym, we will cover this when we are doing physiology, but when you're in the gym, for muscles to contract and relax, right? We call it that power stroke. It requires ATP. So ATP is the currency. It's the currency of energy in the body. So let's start with carbs. You've eaten your carbs, for example, chapati, ugali, what else? I don't know, biscuits, such things, right? So it's when it reaches the body, enzymes will break it down. We've talked about enzymes. Enzymes will break it down to the monosaccharides, right? Because it's only a monosaccharide that can be absorbed by the intestine. Anything bigger than that, it's too, let's say it's too big, right? So for monosaccharides, we focus on the most common monosaccharide, and that is glucose. When someone faints, when someone is having a hangover, they are given glucose, because glucose is it's the most common molecule for us. So how is glucose absorbed? I won't go into that because that's more of physiology. We'll look at it later. But once glucose is absorbed from the body, once glucose is absorbed from our intestines, it will go to the cells, right? Through the action of insulin, glucose enters a cell. And now once it enters a cell, that is where now our glycolysis will start, right? Glucose, number one, it's osmotically active. And when we say osmotically active, we mean that osmotically means it has an effect on osmosis. And when we say active, it means, in short, glucose will suck water towards itself. Like, in short, glucose, you can say also glucose is like salt, right? When you put salt and water next to each other, the salt sucks the water, right? You'll find the water has gone. So glucose is like salt in this case, right? It will suck the water towards itself, or rather it will absorb. I don't know the right term to use, but I want you to picture glucose as that, something that pulls water towards itself. And that is why in a disease, not in a disease, in a complication such as diabetic ketoacidosis, right? Glucose is high in the bloodstream, it's high in the kidney tubules, and because it's so high, it pulls water towards itself. That's why someone with DKA, someone also as a symptom of diabetes, we see polyuria. This person keeps going to the washroom because all the water. So this guy will have polyuria, going to the loo a lot, short calls, and they'll also be thirsty because they are losing water. So I want to take home message number one: glucose is osmotically active. So once it enters that cell, it is essential that it is converted from that glucose to another thing that is not osmotically active, and that is glucose 6-phosphate. So as a that is one important thing you can put in terms of why glucose needs to be converted. It's number one is because it's osmotically active. So it's converted to the glucose 6-phosphate, then fructose 6-phosphate. For the steps, we'll just have to memorize and learn the names of the enzyme, because there's nothing much I can say that can help you. I don't know. I don't have a mnemonic, so I just know that glucose, number one, is the first thing that is formed is glucose 6-phosphate. Then at the very end, you form pyruvate. But if it's an anaerobic metabolism, remember there's aerobic and anaerobic metabolism. So aerobic metabolism, we say oxygen is in sufficient amounts, right? However, for anaerobic metabolism, oxygen is in limited amounts. So there isn't enough of oxygen, in short. So in anaerobic metabolism, well, the last ingredient of glycolysis will be lactate. It will go all the way back to pyruvate, but then because there isn't enough oxygen, it will be converted to lactate. And this is where we say, even when you exercise too much, when someone has run a marathon or has overexerted themselves, they'll be having lactic acidosis because lactate has accumulated in the body. So from the glycolysis, just know that 2 ATP molecules are spent on glycolysis, but it releases 4 ATP molecules. So we spend 2 and then we release 4. That means the net production of ATP, it's that 4 minus the 2 we spent. So in short, glycolysis, after all those steps, it will just give us 2 ATP molecules. Then those 2 ATP molecules, the ATP molecules, those ones are done. Those ones, we will use that ATP. The other thing that it does produce, as highlighted here, it's this NADH. NADH here, we see there is production of this NADH. Now, when we go through the electron transport chain, we'll see the significance of this NADH, and from the carbon TCA cycle, we'll also see NADH again and FADH. Because this NADH and FADH, they go to another electron transport chain to produce more ATP. But we'll see that when we're doing electron transport chain. So there is a rate limiting step in glycolysis, and that is step number 3, when fructose 6-phosphate. Just a second. Sorry about that. So the rate limiting step is this third step, where we have PFK, phosphofructokinase. And I don't know if it was covered before by Seraphine. Seraphine, had you covered what I don't know what we mean by when we say rate limited step under enzymology, or
No, I didn't do that.
Oh, you didn't do that? Okay. Just let's go here. So rate limiting step, essentially, it means rate let's again, just from the definition, rate limiting step. So it means if this step doesn't take place, that whole reaction chain won't take place. That it will stop at that. But if the rate limiting step takes place, then we are sure we will form our pyruvate, we are sure we will form our lactate. Again, on the rate limiting step is also, you can say, this is where you can say this is where the fate of glucose is determined, that this glucose will be going to all the way towards forming pyruvate. So in short, if we want to stop glycolysis, if we want to increase glycolysis, the one place that we should target is at that rate limiting step. Estano.
Oh, sorry Gauss, ulikuwa umesema hiyo rate limiting step is step 3. Imenipita
Yeah,
kidogo.
step 3. Hiyo wenye iko the one with the phosphofructokinase.
Oh, sir, thank you.
Yeah. So okay. So we've said the rate limiting step. If you want to inhibit glycolysis, the best place to target would be this rate limiting step. If you want to increase the rate of glycolysis, the best place to target is, again, this rate limiting step. And that's the only place we are going to look at, where we will also focus a bit on the products of glycolysis, just a bit. So let's go to glycolysis for 1 second. We saw glucose was converted to glucose 6-phosphate, and we reminded ourselves glucose is osmotically active, so it needs to be converted to glucose 6-phosphate, and this is enabled by hexokinase. Hexokinase, Nani mentioned it when she was doing enzymology. Hexokinase, I don't know if someone can answer if it fell under which class of enzymes. We saw oxidoreductase, transferases, hydrolases, lyases, isomerases, and ligases. I don't know if someone can answer at least. I might even use Seraphine, maybe you can answer. Okay.
So hexokinase, like we can see from glucose to glucose 6-phosphate, of course, we are adding a phosphate. So it's what is it called? That's the second class. Wait, it's okay,
transferase, yeah, second class, yeah.
Yeah, second class. It's a transferase, and we also said it's a group specific kind of enzyme.
Yeah, group specific, yeah. So transferase, right? Transferase, simply from the word, from the word transfer, it means we are transferring from one place to another. So in this case, we've transferred one phosphate from ATP, and we've given it to glucose to become glucose 6-phosphate. So it's a transferase. And remember, kinases are the most common type of enzyme we'll encounter here, even when we're doing pharmacology. So kinases, just remember, they are transferases or class 2 type of enzymes. So glucose to glucose 6-phosphate, and then isomerase, we get the fructose 6-phosphate, and then PFK, phosphofructokinase, we get the fructose 1,6-biphosphate, and then we go down, we get all of these products. Now, so now I want us to go back to this rate limiting step. We said it's step 3 of glycolysis, whereby PFK is the one affected. And yeah, here it is. So it's the ATP are the most important allosteric inhibitors. Now, again, I guess in biochemistry, enzymology is everything, and it's so nice that is what we've started with. So allosteric inhibitors. What's an allosteric inhibitor from what Seraphine has discussed? What's an allosteric inhibitor? Stanley, you wanna give it a try? Okay. We'll just so we mentioned two sites when it comes to the basic two sites when it comes to enzymology. There's the active site, that's where the substrate binds, right? And then there's the allosteric site, which means a site different or separate from the one from the active site, right? It's an allosteric, in short, just a different site that is not the active site. 1 second. Okay. We said allosteric site, just a site different from the one, different from the active site. And we saw allosteric site when we were talking about, was it non-competitive inhibition? Yeah, non-competitive. Yeah, whereby the inhibitor binds to that other site, right? That is why the KM was not affected anyway. That's back to enzymology. So here we have ATP and citrates binding or acting as inhibitors. Why? Because remember, glycolysis, we will produce what? ATP, right? And the body always has that mechanism of negative feedback. Negative feedback in terms of, for example, with the sex hormones. Let's work with the sex hormones. We say FSH goes and hits the ovary produces estrogen. Estrogen goes back to the pituitary and tells the pituitary, there's enough oxygen now, you can stop. There's enough estrogen, you can stop your work, right? Negative feedback. Just the same here with ATP. We've gone to glycolysis, we produce the ATP. So when ATP is in adequate amounts, it will go back to the rate limiting step, 2-phosphofructokinase, bind to it and inhibit it. So it will decrease that rate of the reaction. Same with citrate. We'll see citrate in TCA cycle. Then we are seeing AMP. AMP acts as an activator, still allosteric activator. I mean, it's binding to another site, but activating. So ATP will inhibit it. Why? Because this system is producing ATP. So if ATP accumulates, it goes and inhibits it. Then AMP activates this PFK. Then we go and look at now fructose 2,6-biphosphate. Fructose 2,6-biphosphate. So to remind you, PFK converts fructose 6-phosphate to fructose 1,6-biphosphate, not 2,6. Converts it to fructose 1,6-biphosphate. So there's a different enzyme. The enzyme for glycolysis is PFK1. Now there's PFK2. This PFK2, it forms this fructose 2,6-biphosphate from acting still at fructose 6-phosphate, right? But now this, you can say, I don't know how we can put it, but simply this is the statement that when glucose is in plenty, this means that glucose, let's say you've just eaten your meal, you've taken a soda, so that means when your glucose levels are high, PFK2 is activated. Yes. Sorry guys. Yeah, so we were talking about fructose 2,6 biphosphate. We've said it or rather it increases the activity of PFK1. How? Because when glucose is in good supply, you've taken your soda, that PFK2 is activated. When it's activated, we form more of fructose 2,6 biphosphate, and this fructose 2,6 biphosphate activates our fructose phosphofructokinase, the PFK1. So F26BP, fructose 2,6 biphosphate, is an activator. AMP is an activator. Then the inhibitors we found so far, ATP and citrate. Those are inhibitors. So that is it about the rate limiting step. We have the two activators, AMP and fructose 2,6. Then the two inhibitors, ATP and citrate. Then I believe that's yeah, that's it, unless someone has a question. Glycolysis. Or any question, addition, subtraction. Stanley, Shrina. Okay, Seraphine, do you uko ready? You do the TCA cycle, you take it from pyruvate, and then we finish with the electron transport chain.
Yeah, we can continue with the PCA cycle.
Let me stop sharing.
So basically the TCA cycle continuation of glycolysis. So the end product of glycolysis is pyruvate, and pyruvate is now what feeds into the TCA cycle. Although not as pyruvate, it's first converted to acetyl-CoA, which now then feeds into the TCA cycle. Yeah. So the pyruvate will be, it's just, this one is what is it called? 6 carbon chain. These are 3 carbon chain. It's just broken down into, the pyruvate is just broken down into 2 of these now for the TCA cycles. Yeah. Yeah, so now for the conversion from pyruvate to acetyl-CoA, which is what we need for the, what is it called, for TCA. We need what is it called? What are those things? Like we were saying in enzymology, for some of these enzymes, you need maybe a metalloenzyme if it's a metallic compound, or a small organic molecule like thiamine to help activate the whole reaction. So for here, we'll need thiamine, vitamin B1. You can see where we can get it. And of course, if you have a lack of it, you and beriberi will end up being friends. Anyway, yeah, so whether you ask about the TCA cycle, Krebs cycle, they are all the same. And so the TCA cycle happens under, what are they called? Under aerobic conditions. It happens in the mitochondria. So if we are talking about prokaryotic cells in the cytoplasm, eukaryotic cells in the matrix. So yeah, so then, so basically what happens, again, we just keep repeating the same things. So from pyruvate to acetyl-CoA, then the acetyl-CoA ends up being converted into the end product where we get oxaloacetate, we'll get ADP, NADPH, and those are all other things. Let's go to the yeah, so from pyruvate, it's converted to acetyl-CoA, which enters the TCA cycle. Then the whole cycle takes place to just give, it's a, what is it called? It's oxidation of acetyl-CoA to give CO2, but then in the process, there are now other products like GTP, NADP, NADH, 3 of those, 1 GTP and 1 FADH2 are produced in the process. And then also there's ATP produced, which now is actually now what we want, the energy. Yeah, so for the regulation of the TCA cycle, so we have allosteric modulators, covalent modifications, and the supply of acetyl-CoA. And then also, of course, again, some of these, what are they called? Some of the components in the TCA cycle will end up either through feedback mechanism, either inhibiting or activating the cycle to continue as part of the regulation process. So like, for example, well, let's go back to, so like, for example, citrate synthase will be inhibited by citrate. So here, if we have more of citrate, like if citrate accumulates, then it will end up inhibiting citrate synthase through a feedback mechanism. Then that will lead to, like, the whole cycle will let's stop or slow down for until more of that product is consumed, so that again it can stop the inhibition process. And then now alpha ketoglutarate dehydrogenase is inhibited by ATP, succinyl-CoA, and NADPH. Okay, we have to just keep going back and forth. Okay. Yeah, so here, so what we're saying is alpha ketoglutarate dehydrogenase, which is involved in the conversion of alpha ketoglutarate to succinyl-CoA, will be inhibited by ATP, succinyl-CoA, and NADPH. So if this in the cycle, like we are producing energy, the 10 molecules of ATP. So if ATP builds up, then it will inhibit that reaction through it binds to the alpha ketoglutarate dehydrogenase, inhibits that reaction, which stalls the whole cycle. So those are the three. We've mentioned two. So there are three enzymes in this process that are involved in regulation. So one, we said citrate synthase. Which is inhibited by NADH, ATP, succinyl-CoA, and of course citrate, the product of the reaction. They inhibit citrate synthase in the regulation of TCA. The other one, we have said alpha ketoglutarate is inhibited by ATP, succinyl-CoA, and NADH. So when any of those is increased, their levels are increased, they inhibit the reaction, they stall the cycle. And then the other regulation point is here at the isocitrate dehydrogenase. So this enzyme is also affected by the levels of ADPH, which when we have more of it, it increases the activity. Then we have NADH, which would reduce the level of activity of isocitrate synthase. Yeah, so that is there. Those are the regulation points for the TCA cycle. So we have those three. What else was I supposed to mention about TCA cycle, my guys?
There was that mnemonic you could give, the one for I think
my guys, it's
citrate.
Jazz who has said about that mnemonic, it's not me. So the mnemonic is for the steps. So basically we are moving from citrate, isocitrate, alpha ketoglutarate, succinyl-CoA. So guess what was it? Can I
you can say not even citrate, because citrate is the one that we are starting with, right?
Yes.
We say citrate is this citrate is Krebs starting substrate for making oxaloacetate. So let me see if I can annotate. Let me annotate. So we say citrate, which is C, is isocitrate, Krebs starting substrate. So starting substrate for, that's fumarate, making, that's malate, oxaloacetate. So citrate is being associated Krebs ketoglutarate as statin succinyl-CoA, substrate be now the nini succinate. I don't know if you call it succinate, and then 4-fumarate malate oxaloacetate. So you can repeat that mnemonic as for yourself. Citrate is Krebs statin substrate for making oxaloacetate.
Yeah, then of course, once now those products for the enzymes, basically, if you're moving from citrate to isocitrate, you can just look what's the difference between those two structures, and you can easily come up with what is it called? You can actually come up with what is it called? That enzyme, the name of the enzyme, based on the kind of reactions that are taking place to change from one to the other. Or you can just cram, whichever works well. Yeah, so TCA cycle, just as we are finishing, is among cycles, or among the few things, in metabolism, it can either be anabolic or catabolic. Now, for TCA cycle, it's one of those things that is both anabolic and catabolic. Because you're breaking down, what is it called? You're breaking down carbohydrates. But then in the intermediates, you can see at some of the points, we are coming from a smaller molecule and creating a bigger molecule. So it can be both be anabolic or catabolic. Anything else, guys? Anyone has something?
Bagwat has raised his hand.
Hi guys.
Hey.
I just want to add something on what Yasmin and guys have said, that cycle, yeah, and of course gluconeogenesis, which is opposite of the glycolysis. In all these points, they have really elaborated about the control points, and also these control points are again important because of what is required in the body. It all depends on that individual body and what they require at that moment, at that time. For example, when we're talking about the glycolysis, the glucose 6-phosphate which we produced, it's not a must that it will go through the whole process and give you pyruvate. The same glucose 6-phosphate and also the fructose 6-phosphate can also go into making your DNA and RNA, and that's where we'll elaborate on the pentose phosphate pathway. And this, so it depends on what the body requires. If you need to make DNA, RNA, the same glycolysis process goes into the pentose phosphate shunt. The same thing with this citric acid cycle. if you look at most of these molecules, yeah, they will also form. If you're just looking at structure, you'll see that some of these molecules will be used in making some of the amino acids also. So later on in the same biochemistry course, when we will go to the protein metabolism, you'll see some of these molecules going from the citric acid cycle into protein metabolism also. Yeah, so it all depends on what the body requires. That's what I wanted to add. Thank you.
Thank you very much. Thank you very much.
Yeah, just before you wind up the meeting. Oh yeah, we said the end product of glycolysis was pyruvate, and glycolysis was taking place where?
The cytoplasm.
Yeah, in the cytoplasm. But then again, you've said TCA is happening in the mitochondria. So if pyruvate is uko kwa cytosol, we need it to get inside the mitochondria now for TCA to actually work. So there's what is it called? Whatever. A pyruvate translocase that transports pyruvate into the mitochondria. It's a sympod. So it basically transports, what's it called? Pyruvate and hydrogen, so that now TCA can happen inside the mitochondria. Okay, guys.
Is that the Cori cycle, or I'm confusing it with something else?
No, yes, the Cori cycle, the TCA cycle, the Krebs cycle, it's all the same thing.
So Cori cycle is not the one that you've just said where you transport the pyruvate or something into the mitochondria, or
I thought they are all the three of them are the same. What is it called? The same thing. Because glycolysis happens in the cytosol, and we need to transport, like we need to, TCA is happening in the mitochondria, glycolysis the other side. So then if we're using products from one, then we need them where they should. Anyway, Gaius, I think they are the same thing. Gaius, nadanganya watu hapa.
I think Hiral can advise us.
I'm not sure myself. That's why I asked.
The Cori cycle is different. Cori cycle is different. Cori cycle is now, it's where you see when you did your what do you say? You see when you do anaerobic metabolism, yeah, which happens in the muscle, that pyruvate no, sorry, when you did anaerobic when you do anaerobic respiration and you get lactate in the muscle, yeah, that lactate now can move back into the liver, and that lactate can be converted back to glucose. And that is Cori cycle.
Okay.
You see, the muscles will always require glucose, yeah, for metabolism when you're doing exercise. So what the body does, and if there is no glucose, what the body does is takes back that lactate and converts. So from the muscle, the lactate goes into the blood, from the blood back to the liver converts it back to glucose, gives it back to the muscle. That cycle is the Cori cycle.
Nice. Thanks for the clarification. I think we'll cover the Cori cycle more in detail when we're looking at biochemistry of specialized tissues, where we look at the muscles, right? So, Seraphine, can I finish up with electron transport? There was something you wanted to...
Oh no, that's yeah, we're good. You can
Ah,
continue.
you're good. Second, let me be projecting my screen.
Sorry, let me just stop sharing.
So electron transport chain. So let's start with the basics. With what we know, right? We saw in glycolysis, we had somewhere we had NAD plus, and then we converted that NAD plus to NADH, right? Somewhere in the citric acid cycle, there was somewhere we had FAD plus, but we converted that FAD to FADH2. Now, taking you back to chemistry, right? Where we covered redox reaction, right? Oxidation and reduction. Oxidation, we said simply oxidation is something has lost electrons, right? But reduction, something has gained electrons. So maybe someone can answer, because this is at least revision. Maybe Coach. So if something has moved from NAD plus to NADH, has it been oxidized or has it been reduced? Anyone in the audience can answer. We've moved from NAD plus to NADH. It had a plus charge, but then we've moved it to become a neutral molecule. Would we say that is oxidation or reduction? Trials, Kristen, Mike, Scooby-Doo, Kevin Kim. Aye. Tough crowd. Anyway. So we'd say it's reduction, right? Because it has moved from, or rather, essentially it has gained electrons. That is why it had a positive charge. Now it's a neutral charge, meaning it has gained electrons, right? Yeah, for example, if we move ion 3 plus to ion 2 plus, that ion has been reduced, right? It still has a positive charge, but it had more positive charge on the other side. So in short, it's a reduction, right? And what is reduction? Jambi explained, reduction is simply something has gained electrons. When something gains an electron, we say it has been reduced, right? So because those are the basics of the electron transport chain. So we are seeing, let's look at the word, the wording of that chain or of that system. Electron, right? Electron, we've covered that NAD plus to NADH, it has gained electrons, right? And when we were covering glycolysis, we said we will see this NADH again. Yeah, we said it is that as much as glycolysis in itself has just given us 2 ATPs, glycolysis can't just be giving us 2 ATPs, yet we depend on it on energy. TCA can't be giving us that few number of ATPs, yet we depend on it. It has to give us a lot. So, and this is where the electron transport chain comes in. We formed NADH, we formed FADH. These things we said they were reduced. Reduction, we said it's whereby a substance, a molecule, a compound, what you want to call it, has gained electrons. So in the electron transport chain, we are coming to release these electrons, right? We're coming to release these electrons, and once we release them, we are able to regain our compounds. Let me annotate here. Yeah, we see NADH, we've gotten back our NAD plus, we've gotten back our FAD, right? Now this one goes back to glycolysis, this one goes back to Krebs cycle. NAD can also go back to the Krebs cycle, right? We will be reusing these things, right? We'll be reusing them. So so now so in short, the NAD, the NADH, the FAD, what we can say is they come to the chain, or rather they come to this system to give up their electrons, then they go back to where they are found, that is in glycolysis, in TCA cycle, right? So I want us to explain, I want us not even to explain, rather to cover this the process of the electron transport chain, and then we will call it night, right? So in the electron transport chain, just first thing you need to note is that it contains 4 complexes. Is this one complex 1, complex 2, complex 3, complex 4? They are even numbered. Complex 1, 2, 3, and 4. Then at the very end, this one is not a complex. This is an, we say this is an enzyme. This is ATP synthase, right? Remember we said what? ATP is the currency of energy in our body. So at the end of the day, we want ATP. ATP is what we want. Now this step is taking place inside the mitochondria, or rather, we can say the inner mitochondrial membrane. I don't know if it's, and then the outer mitochondrial membrane. So there's this intermembrane space. So you let's keep it at that, whereby you can see that intermembrane space, because it will be relevant once we are discussing these steps. So in the first step, we've seen NADH has come in, right? NADH from glycolysis, from TCA, has come to the here to the inner mitochondrial membrane. It has said to complex 1, yo, take my electrons. Me, I'm going back to glycolysis. I don't belong here. So it gives its electrons to complex 1 there, and then it goes on its way, you know. Then again, FADH2 comes from TCA cycle, which has just happened in the mitochondria. It hasn't traveled far. It gives its electrons there to complex number 2, and then it goes on its own way, you know. And those ones, they say we have done our job. Our job was to do what? Our job was to take the electrons to the electron transport chain. What does the chain do with it? We don't know. We don't care. We are going back to glycolysis. We are going back to the TCA cycle. We grab more electrons. We bring them back here. And then the chain does what it does best. So once they've given, now that's the end of that's the end of NADH and FADH2. Now what will be following is the electrons, right? It's the electron transport chain. So these electrons we've seen. Now let's follow. NADH gave, now they're in complex 1, and also FADH gave. Now complex 1 and complex 2, they hand their electrons to this ubiquinone. Something I forgot to mention. This complex 1, 2, 3, and 4, they are stationary. They do not move. They are there to stay, right? But this ubiquinone, that one can move, right? So it's complex 1 gives it its electrons. Complex 2 also hands its electrons to ubiquinone. Once they give it to ubiquinone, where does ubiquinone take them? To the next guy, right? This is it's a chain, as you said, it's a chain. So it gives them to complex 3. Okay, it gives the chain to complex 3. Now this is where I know we'll talk about this hydrogen that has left here. We'll talk about it just here when we're talking about complex 3. But now, hey, sorry, let me take a breath of water. Aye. We're back. Sorry about that. So at step 3, or rather, no, not at step 3, at this one written number 3, or at complex here, this step 3, here, and this is where oxygen becomes essential. Oxygen becomes essential in this at this time, because note that at the very end, oxygen will act as a what? Electron acceptor. Oxygen will accept all these electrons. If we can fast forward and follow this chain of electrons, we'll see they travel from complex 1, complex 2, they give it to ubiquinone. It goes to complex 3. Complex 3 gives it to cytochrome C. Cytochrome C gives it to complex 4. Complex 4, we are seeing it, those electrons will react with oxygen here to give water. So in short, oxygen is the one that will accept all of these electrons. That's why oxygen is important. Without oxygen, you die. So keep in mind that oxygen, because you can see we even number it as our step 4. That at the end of the day, these electrons, where will they be going? They will be going to oxygen. So once we give these electrons to oxygen, we go to the story as old as time itself. Oxygen plus hydrogen will just give you water, right? Oxygen plus hydrogen will just give you water. And now, where the question comes, hey, where are these hydrogens? Where did these hydrogens come from? Remember, these are the hydrogens from NADH. It changed to NAD plus, went to the glycolysis, but it left its H plus. H plus is what eventually will react with oxygen to give water. So just keep that in mind. Just keep that in mind. That at the end of the day, what they'll also be formation of water. But let's go back to our transport chain. So as these electrons are moving through this complex 1, complex 2, complex 3, we know they are releasing energy. We said an electron on its own will release energy, right? And this released energy can be lost as heat. But in the mitochondria, remember, mitochondria is the powerhouse of the cell. We do not waste energy in the mitochondria. So the energy that is released when these electrons are being transferred from one complex to another to the other, right? That energy that is released, it's utilized by complex 3 and by complex 4. It's utilized by these complexes to do what? To transport hydrogen into the intermembrane space, right? That so as this electron is working, it's releasing some energy, and now the complex, these complex 3 and 4, they're like, hey, let's chase away these hydrogens. So the complexes, you can see they push the hydrogens to this intermembrane space, and now hydrogen accumulates in that on the intermembrane space, right? So remember this, where this inner mitochondrial membrane, it's a barrier. It's let's call it, it's a semi-permeable membrane. So we've been pumping through the energy that the electrons are releasing when they are walking around. We've pumped hydrogen ions into the intermembrane space. And now the hydrogen ions, they've accumulated there. And now we go back to nature. As our hero once said, you can't defeat nature. If you destroy nature, it will destroy you, right? Wangari Maathai. Now, nature, basically, stuff will always move from areas of high concentration to areas of low concentration. That is just nature. You can't change nature. You can't fight nature. So we've been pumping these hydrogen ions into the intermembrane space. So it means there'll be a high concentration of hydrogen ions here and a low concentration on the other side of the intermembrane space, right? High concentration here and a low concentration on the other side. Now, this is where the magic happens, ladies and gentlemen. This is where the magic happens. This is how we make ATP, by utilizing the most simplest of concepts. That is stuff moving from high concentration to a low concentration. Because now we've created a gradient, right? A gradient. And remember, a gradient basically from high school maths. This gradient, let's say it's looking like this, but we want it to move from this high to this low, right? That's the gradient we've created, because they are more concentrated on one side and less concentrated on the other side. So once now these hydrogen ions, now they will move through this channel. Let's not call it a channel. They'll move through this last one. Remember, this is not a complex. We call this ATP synthase, right? So as these hydrogen ions are moving from that area, or from that areas of high concentration to areas of low concentration, this flow of hydrogen ions, they will act as a source of energy. Or you can say that this flow of hydrogen ion, they will activate this ATP synthase. They will activate it. It's like they'll activate the ATP synthase, and now ATP synthase will be able to combine ADP plus a phosphate to make ATP. It will activate this ATP synthase to be able to make our ATP. So simply think about it as what like this anything now to summarize, just think about it as these things are moving. As ions are moving, they release energy. So as these electrons were moving, they were releasing energy. That energy was harnessed by complex 1, complex 2, complex 3, and complex 4 to pump hydrogen onto the outer side of the intermembrane space. And we created a gradient. We created high hydrogen on one side, low on the other side. So when the hydrogens found a chance to move through where this ATP synthase is located, as they were moving through very fast, right? Moving fast, right? That's kinetic energy. That's energy. There's some energy released. They activated that ATP synthase, and it was able to form, as the word suggests, it was able to form ATP, right? And I want you to note it's synthase and not synthetase, because a synthetase uses energy. Here we are not using energy. We are not using ATP as a source of energy, because it wouldn't make sense for us to use ATP to make ATP. Then the result would be 0, right? So I think, yeah, that's it, unless someone has a question. I've tried to summarize or to explain it as best as I can. Anyone with a question or even an addition, maybe to summarize it better, the floor is yours. Maybe Coach. Devayani, Shafi, questions.
Yes,
If there are any
guys.
questions, we can questions, additions, comments. Have something to add.
Yes, thank you.
You've explained. I'm happy to hear that. Happy to hear that.
No
Any
question. No question from my side.
no
Oh
question
yeah.
from your side.
Daya, so
Mhm.
what is it called? The electron transport chain, since it involves a lot of oxygen, which ends up being reduced to form water and such.
Mhm.
So sometimes that whole process is not well, what is it called, regulated, and you might end up forming superoxides. So there's also that part where the superoxides are catalyzed and everything to just make sure you don't have an excess of those things in the system. So if you form the superoxides, they are catalyzed back into the whole oxygen and water, which can just combine or do whatever they do.
Yeah. Oh, then from Betty has ever asked this question, and cyanide poisoning. He said that cyanide poison, it acts on the electron transport chain, and so just again, I would go deep, just because we've mentioned it. Remember, we said all this complex 1, 2, 3, and 4, they are fixed, right? They are not moving. But ubiquinone, that is coenzyme Q, or ubiquinone and cytochrome C here, these ones can move. These ones, they are not tied down. So what does cyanide do? Cyanide binds to this cytochrome C, right? Once it binds to this cytochrome C, essentially we stop the electron transport chain from there, right? Can't go on. So once we've stopped it, we are not able to produce ATP. We deplete the ATP we have in our body. And as such, acidosis will result because lactate will build up, and eventually you'll just die. But in short, cyanide poisoning, it comes and hits our cytochrome C. You take cytochrome C out, you've killed the guy. So just if your cyanide poisoning acts on which system, it's not glycolysis, it's not TCA cycle, it's on the electron transport system. Yeah. Antidote for cyanide poisoning, as of yet, there isn't really the perfect antidote, but the reagent they give, or rather the they give, is the hydroxycobalamin, because hydroxycobalamin can combine with cyanide to form non-toxic stuff. But it's just I wanted to remind you, cyanide, it works on this part of the cycle. So the next time you're with your special person at the cinema, and the spy movie, someone is killed through cyanide poisoning. Tell your person, I know how that guy died. I bet they'll really be impressed. I'd be impressed. Thank you. That's it for me.
Oh, that's it for today, guys. We'll send tomorrow. Tomorrow we'll send now the topics for Wednesday and Thursday, so that we are not, yeah, so that we don't ambush you guys like today. Sorry about that. Okay, we can end here.
Have a good night.
Night, guys.
Wait, Seraphine.
Yes.
No, okay, I had a question I forgot to ask,
Okay.
but it was on enzymology. That what's the
Okay.
difference between a cofactor and a coenzyme? I remember Betty ever asked someone that question in orals, and I laughed at the person because they mumbled. Yeah, so yeah, please, the difference.
Between a cofactor and a coenzyme. Is there, okay. I'm trying to figure out if I think of any, but honestly, I'm not so sure, but coenzymes, coenzymes are organic. Coenzymes are organic. Then cofactors can be, I don't know, both organic or inorganic.
Oh, like the kinametals,
Yeah,
kinamagnesium.
the kinametal ones, they can be, the kinametal ones, they are for sure cofactors. But now when they are talking about these other ones, the organic molecules, okay, acha tu nikwambie ukweli guys, let me not lie to you, but I think cofactors can be both organic or inorganic, but coenzyme is specifically an organic molecule. But I'll confirm and tell you kama ni kweli, but that's what I think. Coenzyme is specifically organic. But I'll check. Wacha tusidanganyane, I will check and tell you. Kama ukipata before I do, you will let me know.
Sawa. I will see you tomorrow, bright and early.
Okay, tomorrow.